All right, welcome back. We are beginning a new unit now, our unit on reasoning and proof, as we look at some more of the basics of geometry. Last unit was on basic terminology that we'll get to. This is on the basic line of thinking as we begin to work with proving things and proving theorems in geometry. So we need to learn about how to use our reasoning skills. First skill we have is called inductive reasoning, which is based off of observation. Okay, so we take what we see in a pattern and see if we can apply it to future examples. So let's begin by working on our inductive reasoning skills by looking at a visual pattern. Okay, you see the first figure, the second one, and the third one. So we see if we were to draw the fourth figure, what would that look like? Well, we know it's going to be a circle. We see it's 2 pieces, 4 pieces, 6 pieces. So if it continues in that pattern, this next one will be 8 pieces. See if I can draw that. Well, you get the idea. And then we have 1 piece shaded in each one. So we'll have 1 out of 8 pieces shaded there. Okay? Don't you love my wonderful artistic skills there? Anyway, so inductive reasoning is taking observation of what we see and continuing the pattern. Okay? We can do that with a number pattern as well. Okay? So you'll recognize this as a sequence in algebra. So if I were to continue the sequence, what would the next 3 values be in that sequence? I'll give you some time to think about that one. Okay, so as you took a look at the first 4 terms in the sequence, could you figure out how they were changing? It appears that as we're going from one number to the next, we're multiplying by 3. So if we continue that pattern, we'll just multiply those values by 3. Take out my calculator. Negative 189 times 3 is negative 567. Okay, multiply that one by 3. Negative 1701, and multiply by 3 again. And we get negative 5103. So that would be the next 3 terms if it continues in that pattern. Okay, so that's how we take a number pattern and use our inductive reasoning to continue that pattern. Okay, so skills that you've used already in algebra, but we're just focusing on this line of thinking. Now we're going to take a look at how we form a conjecture. Conjecture is a fancy word for educated guess. We're making a statement based off of what we've observed, but it hasn't been proven yet. So here we're given 5 collinear points. So remember we talked about collinear last time. Points all in a row, in a line. We want to make a conjecture about the number of ways we can connect those different pairs of points. So what I'm going to do, and as you've seen, I've created a table on the side here, is I'm going to see if I can observe a pattern when I make a simpler problem. So 5 points is kind of a lot to take a look at. I want to see if there's a pattern to this and go from there. So if I have 2 points, there's really only one way to connect those 2 points. Okay, so I can only connect from one to the other. Okay, if I have 3 points, I can connect the first to the second, first to the third, second to the third. So there are 3 ways to connect those. If I have 4 points, first to the second, first to the third, first to the fourth, I could also go second to the third, second to the fourth. I could also connect the third and the fourth. Okay, so if we take a look at those, there's 1, 2, 3, 4, 5, 6 connections there. So do I start to see a pattern? 1 with 2, 3 with 3, 6 with 4. I see that this one got 2 more. This one got 3 more. So if the pattern were to continue, this one would have 4 more, which would be 10. Let's see if that holds true. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, So we made a conjecture based off of an observation. We can test that conjecture to see if it works out. So we'll do that again with another example. It says numbers 3, 4, and 5 are called consecutive integers. Make and test conjecture about the sum of any 3 consecutive integers. Well, let's just see what happens when I take 3, 4, and 5. When I find the sum of those 3, 9, I get 12. Okay? Well, why don't you try a couple of your own? See if you can come up with a pattern or an observation based off of what you choose. So try different sets of consecutive integers and see what you get. Okay, so here's a couple more examples. You can compare with the ones you had. What did you get for your conjecture? I noticed that whenever I added them up, it appeared that they were all even numbers. So I tried another set, 14 and 15 and 16, and that gave me, that gave me 45. So that conjecture didn't hold because now we've got an odd sum. Okay, but then I started to notice something else as I compared this number here. And maybe you noticed the same thing. Maybe you noticed it before I did. That it appears that the sum is 3 times more than that second number. And so that was my conjecture. And now I'm going to take a look at that and see if it holds true. I need to test it out. And now when I test it, I need to try some different variations. Like throw a negative and a 0 in there. 0 times 3 is 0. That works. Throw a larger number in there. See if it holds true with large numbers. Well, 101 times 3 is 303, so that still works. Throw negatives in there. See if it works with negatives. And it still does. So once you get a conjecture, you need to test it out with many different types of numbers. Here, my first conjecture that they were even worked because, well, I started with all odd numbers. You got to change things up a little bit. Okay, so if you are looking at a conjecture, in order to show that a conjecture is true, you need to show that it works for every single case. If you can find that there's just one way that it doesn't work, that's known as a counterexample. That shows that the conjecture is false. So as we look at the previous example, my conjecture was the sum is even. Well, here's my counterexample, 14, 15, and 16. That disproves that conjecture. Okay, so all it takes is one counterexample to prove a conjecture wrong. So a student makes the following conjecture about the sum of two numbers. Okay, find a counterexample to disprove his conjecture. He says the sum of two numbers is always greater than the larger number. Okay, so for instance, if I take the numbers 4 and 17, 4 and 17 is equal to 21. We're saying the sum of those two numbers is greater than the larger number. So is 21 greater than the larger number, which is 17? That is true. Does that work in that case? Can you find a counterexample, one that doesn't work in that instance? Go ahead and pause it and see if you can come up with one. Okay, I've provided two counterexamples. Remember, you only need one counterexample to prove that the conjecture is false. But I chose to use 0. 0 plus 5 is 5. The sum 5 is not greater than the larger number 5. It's equal. So that blows the whole conjecture out of the water. It doesn't work. If I were to use a negative number, negative 4 plus 6 is 2. The sum of those two numbers, 2, is not greater than 6. So I could have used either of those examples, or maybe you had an example at work there. But all we need is one counterexample to disprove a conjecture and show that it's not going to work. Okay, so conjectures can come in many different formats. Here are some conjectures. See if you can come up with a counterexample as we're going through these. All sports have a score that starts at 0 and goes up. Well, I can think of one. Golf. Golf starts at 0, but sometimes your score goes down if you're a good golfer. If you're like me, then your score does go up, but some people make their score go down. No U.S. state has only 4 letters in its name. Well, here's a couple counterexamples. Ohio, Iowa. I can't think of any others at the top of my head, but all we need is one. Nobody in this classroom has more than 2 brothers or sisters. I'm sure some of you have more than 2 brothers or sisters. 4, all the students in this class are 16 years old. I'm sure some of you are 15 or 17, maybe even 18. 5, none of the food served at lunch tastes good. Well, I'm sure you've got a favorite food at the cafeteria. 6, intersecting circles must intersect at only one point. Well, that's possible, but what happens if we have like the Olympic rings? We're hitting at 2 points. Okay. 7, no even numbers are prime. Well, 2 is an even number and it's considered a prime, so there's my counterexample. Nobody in this classroom owns a dog. I'm sure somebody does. All quadrilaterals are squares. Well, not necessarily. I could have a parallelogram. Okay, so you get the point. We could go through a few more examples, but the idea here is we're just finding a counterexample, something that proves that it doesn't always work in every situation, and that's all we need to do. So, to recap, we just learned inductive reasoning, which is basically taking a pattern and continuing that, whether it's visual or numbers, whatever the case may be. We're looking to find once we see the pattern, make a conjecture, an educated guess, and test it out to see if it works. If we can find a counterexample, we know that that proves that that conjecture is false. Okay, we'll look at other ways to prove in the coming days, but for now, you have some practice problems to do, and as always, solutions are online. Have a good evening or good morning or afternoon whenever you're watching this. We'll see you in class. Bye.